So years and years go by, and we're at Morehouse in the lab, load cells come in, and we have problems. And when we have problems, we go into this diagnostic mode. Well, what could be wrong with it, right? And then everybody does things differently depending on what they think might be wrong. And in the end, when you have everybody doing things differently and not a standardized process, you're spinning wheels sometimes. Hey, did you try this? Did you try crimpling the cable? Did you pin it out? Did you check the batteries? And you start asking all these questions and back and forth to one another. And sure enough, somebody says, oh, I didn't try that. And then that ends up being the problem. So over the years, we've developed this 7-step process for troubleshooting a load cell. Now, this is a revamped version of it. We had a previous recording, but we think this one's a little bit better, a little more clear, a bit more advanced as far as things go. And the hope is to give this webinar is to save everybody's time, right? Through the education, through this, you guys, gals, techs, whomever's out there listening, you can take this information and make it your own. We can share the PDF with you. We can do all this. This is the guideline that we feel works the best for troubleshooting a load cell. And hopefully the half hour, 45 minutes to an hour you're spending today, hopefully the next time you have a problematic load cell, you'll save that by just attending the webinar. That's our goal. So a return on investment. Well, your investment is time, and we certainly appreciate you being with us today. And thank you, Heather, for the introduction. Our purpose here is we create a safer world by helping companies improve their force and torque measurements. And we do that through these webinars. And we also like to help people become more efficient. Because if you're more efficient, that benefits you, it benefits your customers, it benefits everyone in industry. And with those efficiency gains, hopefully you can take more time to concentrate on improving the business, improving what matters, empowering employees, all the good things that make good technicians, power them to make the better decisions and help the customer base. So that's the hope. As with always, I am very reachable. The phone here is 717-843-0081. Your preferred contact method, if it's email and you have questions, you shoot me an email. Also on LinkedIn and Facebook. LinkedIn would be email, phone, and LinkedIn are all good. If anybody wants to LinkedIn message me, no, I don't check that as frequent as email or phone, but that's usually a day response. And feel free to connect. As we post different things, beneficial things, this troubleshooting guide is on LinkedIn as well to access it. So, outcome. Really hoping to standardize your process. If you were like us, as I said, it was a bit of disarray, asking questions, doing this. So hoping that people can understand how to troubleshoot the load cell for errors, including overloading, and use a load cell tester for diagnosing problems. The load cell tester is something we will talk about. It is a very, very good tool. At the very least, someone should have a handheld multimeter in the lab for trying to diagnose problems. But we'll go over that. So the agenda is load cell basics, 7-step process for troubleshooting a load cell, overloaded load cell, and using a load cell tester to diagnose problems. So basics of a load cell. When we talk about a load cells, we're often measuring strain, and that's the amount of deformation of a body to applied force. More specifically, strain is defined as the fractional change in length. And, almost force and torque transducers, they use these things called strain gauges. And when laid properly and done right, that allows you to put forces or torques on the various cells, and that sensing component will output typically a millivolt. Most of them are output a millivolt. And we issue a lot of millivolt per volt reports with the ratio measure, so it's taking the millivolt and dividing it by the DC voltage. And that's how the circuit is. So it's a device whose electrical resistance varies in proportion to the amount of strain in the device. And to measure small changes in resistance, strain gauges are almost always used in a bridge configuration with a voltage excitation source. Most load cells or force transducers use a series of 4 resistive arms with an excitation voltage that is applied across the bridge. This is typical. We get asked questions here like, okay, what's important, and what's really important here is that the lab doing the calibration knows what you're using. So that being said, if you're using, we have an instrument called a DSC. It's a USB powered device. It produces a 5-volt DC output. If you're not sending that with your equipment for cal, which you absolutely should, if you're not doing that though, the lab should not be doing a 10-volt DC excitation. They should be doing a 5-volt DC excitation. So really important to match the excitation and waveform. The best practice is just send the indicator in, marry things as a system, send it all in together. However, just want to let people know there is a difference. There are different meters, battery powered versus DC versus AC. There's a difference in output. So interchanging meters is something that we try to elaborate on, and we in our classes to say don't do it. There's a lot more that needs to be done, and measurement traceability needs to be established, or metrological traceability needs to be established. So we're gauging a load cell, and when gauging, you also use some dummy gauges and things to eliminate temperature effects. And that's one thing we see a lot of where manufacturers may not have temperature comp their load cells. And that's, again, this is another thing, not in this course, but I'm just adding a little bit to it. If you ever were curious about that, in the dead of winter, if you're not in the South, you could take a load cell into the lab before you warm it up, test it, see what it reads cold, acclimate it for a day or two, and test it again. If you're not getting close to the same readings, it more than likely may be that the load cell isn't temperature compensated. So that's a quick way to check. Here's our old million-pound standard. What we did, just part of manufacturing load cells. We used a specialty material, Viscount 44 bar stock. Then we tinned the strain gauge solder tabs, wired the Wheatstone bridge of the load cell, lots of wiring there. Removed excess solder flux, a ground wire added. If you ever see load cells that kite or are very unstable, it might be because they're not grounded properly, and the load cell tester can test that. And then at the end, preparation for testing. Then how the load cell actually works, the signal is converted to a visual or numeric value by a digital indicator. When there's no load on the load cell, the two signal lines are at equal voltage. As load is applied, the voltage on one signal increases very slightly, and the voltage on the other signal decreases very slightly. And we're just measuring this difference, and we're measuring it with an indicator. Here's a picture of a Hattie. This is a high accuracy digital indicator. That's what we chose to name this indicator. And this uses a USB from the computer and has a very different excitation. You measure it about 4.3. Doesn't matter. Now, for everybody, the voltage doesn't matter as long as it's consistent and as long as it's enough to power the gauge. But 4.3, 5, 10 volts DC, all are good. All are good excitations. It's just the consistency is the key. So that being said, here's our 7-step process. And I realize a lot of people may want the PDF of this. And this is flow charted, right? 1, 2, 3, 4, 5, 6, 7. They're there. They're in green. They might be a little difficult to read. Hopefully on your screen you can see. But this is very much a process flow, right? Is there visual damage? Yes, no. And here we have contact Morehouse to discuss options. We'll help you. Regardless of the manufacturer, we can help you. Does it power on? Yes, no. Is it performing mechanically? Here's the things. Does it power on? No. Check connections, batteries, voltage, current. I cannot tell you how many times we've set up instruments and forgotten to put the batteries in. It's very frustrating when you do it. As a tech for 15 plus years of my life, you have those moments where you just forget. We're all human and we all fail, so it's not a huge deal, but it is frustrating when you do a large setup and your clevis blocks the connection for the batteries and you have to pare things down to just put the batteries back in. So it's something that with your techs, if you have, I'm almost positive some have probably forgotten to do that, but it's always good to check first. There's some big time savings in that. If it still doesn't power on, maybe discuss options. Sometimes the discussion of options are replacement options. depending. If it's an old meter that's 20, 30 years old, or an old load cell that's 30 years old, maybe a replacement. There are some load cells that can be re-gauged, though it just depends on the size and the capacity, and that's something we can have those discussions about. But yeah, then mechanically, our adapters bottoming out, and we're going to discuss these in detail. I have pictures to go through them, but as you can see, there's the process. So visual inspection. If it is damaged, contact Morehouse to discuss options. Here, this is a great picture. One load cell works perfectly fine and the other does not. Do we need to even go any further after we see this? You can see that top cap is just overloaded. It's not going to be able to repair. It's smashed. This is one of the worst ones that I've seen. I've seen load cells pulled apart. Usually people don't question that, but you see some stuff like this on occasion where people are like, can it be repaired? The answer most likely is not, and we'll go over why, but this one's easy, right? I don't need to check cables. I don't need to do anything else here. And if you know, everybody knows which cell is damaged in this situation. Does it power on? Here's where a multimeter can be useful. I mean, and here's where you may want to buy a good one. There's cheap multimeters that are, $5, $10. You can get them at, various places. And then there's some that are still cheap, like in the $25 to $30 range, that work a lot better. So you get what you pay for. I had one of my hobbies is rebuilding pinball machines, and I had one that cost me like 3 hours because I'm taking voltage measurements and nothing's making sense. And here it was a $5 multimeter that was a giveaway that my mom gave me for Christmas, and I threw that one immediately in the trash can because my time is worth more than the free giveaway multimeter that doesn't work. So think about that when you're purchasing one if you do not have one. And you can buy relatively inexpensive ones, but if it's too good to be true, it often is, and the $5 ones likely aren't going to cut it. So, maybe the $20 to $25 budget. But here, it's pretty simple. You can check the batteries. And when we give this class live, we go over a whole section on batteries. Right now, there's a Facebook post on batteries, because we've actually observed as batteries discharge, the readings on some of these meters are drastically different than with a discharge battery than with a charged battery. So something else to check, we've got into the habit of replacing batteries when a customer sends something in new. So that is the most repeatable condition when something comes in. Prior to adjustment, put in new batteries and see if it really needs adjusted or brought in to closer to the nominal value when you have new batteries. Some meters compensate, some do not. There's a whole list. We don't know them all. So we just figured instead of doing studies and everything else that would take years, that we just replace the batteries, so we're sure. And we've done occasions. We still do the occasion. Hey, I wonder what happens if we use the old versus new batteries. And in one case, we actually found that the instrument needed adjusted with the old batteries, and this was pretty recent. It needed adjusted. We put the new batteries in, and it was spot on where it needed to be, or close to where it needed to be. So that's a lesson. But yeah, verify that the batteries have enough voltage. If they deplete too much, it may not power on. Check the voltage and check current on the power supply. That can be done with a meter. Current's one you may not get into checking. That's more advanced diagnostic. As soon as you have that, it could be that can be some internal components that are wrong if you have other things. So, is it performing mechanically? This is a fun one here, and you can see if you look at this. If you look at this here, I'm trying to highlight this section, and you can see where I'm scribbling yellow. This is the threaded rod adapter that I'm coloring yellow here. Sometimes these load cells, and not sometimes, if we look at the internal piece of the load cell, there's in the base, right? This has a tapered base. There is a compression stop. And if we're looking at this, it's just a little, it's about right here, and it's threaded in, right? And sometimes in manufacturing, someone threads it a little too far in, right? Or they put it in and it needs to be turned down, and that's usually done from the other side of it. Sometimes it happens, where as we engage, and actually if this is the base, our threaded stop is way here. So if that correlates to this, our threaded stop is right here, and this is all thread. So that being said, if that threaded stop is a little high, and this load cell output is 2000, 2 millivolts, sometimes it might bottom out at like a number like 99980 and not get to the 2 millivolts. In that case, this is a mechanical problem. The other part of it is this threaded adapter here. If we jam this too far down, you won't get this from Morehouse because it's all tested here. Though this is something that we've observed and seen from some other manufacturers. If this is too far threaded down, or then it's going to touch that, and there's a way to readjust your threaded adapter. That being said, if this piece right here comes out, it drastically changes the calibration. So the device needs to be recalibrated if you do have a problem where something is bottoming out. So yeah, and there's the additional pieces there. The thread should never be removed. It avoids the calibration, and we see a lot of people doing that. It could cause the output to plateau. If the threaded adapter has been removed, the cell will need to be calibrated again. For whatever reason, we see people taking these adapters out, and some of them say, hey, I had a space constraint, I thought I could just take it out. No, it's integral to the load cell. Varying the thread depth will change the output quite drastically, so don't take that out. Our adapters bottoming out, that's more of that. If an adapter is bottom out, integral, then contact Morehouse. That's one where it needs recalibration. We done torque everything, take it apart, and clean it. Sometimes you can get dirt and debris in there. We can blow them out. Sometimes it's as easy as that. We had one load cell that just wasn't performing in compression and grade and tension. That's usually a sign that an adapter is bottoming out. If it performs grade and tension and then compression, if the output plateaus, that's a sign. The one we had that was problematic had dust and dirt in it. And again, that was from something a customer did. They took everything out, took it apart, and when they got it back together, we found some dirt in there because they didn't blow it out. Are all wires connected to the load cell meter? This one's it happens quite a bit, where like during shipment something came loose, depending, a back panel might have got smashed, someone might have not packed it properly. So what we're just going to do, this is another visual type inspection, and then we're going to get the multimeter. So we're going to first check and make sure all the leads, all wires are properly connected to the load cell meter. If the load cell is new and you wired the cable, verify everything is wired properly. Cannot tell you how many times people switch A and B, A and D. It seems to be pretty easy to say, hey, the red one's pin A and it goes to pin, the red one's A on the load cell and it goes to pin 7 on the meter. But lots of times people change them. It's just, they think they have it and they're one off or something like that. It's real easy. So that one's an easy check. The harder one is the intermittent problems. So if you're calibrating a load cell and all of a sudden numbers are kiting or jumping on you when you move it, chances are you have a connection that is problematic, right? You have a break in the cable that is shorting or is coming open. More than likely it's coming open. Load cells very rarely short unless there's something major that's shorting both lines. But more than likely a cable's been nicked. Chances are someone packed the load cell in shipping and wrapped. We see a lot of people that wrap the cable of the load cell, big heavy load cell, integral cable, and it's all wrapped together, and they put it in foam, and then UPS or FedEx or somebody else, they transport it, it starts rattling around, and that weight against the cable is sometimes enough to ding or sever cable. And in instance of being severed, the load cell shows up to our door where the cable's completely, it's really obvious. In the fact that it just got nicked, you kind of have to go down the cable. And what we do here is we check for continuity, because sometimes you see a ding in the cable and like indented, and you don't really know what that is. So by checking for continuity, often this is easier with two people. You pin one side to the other, and then you have somebody bend it. And what, if it's intermittent, here you can see the tension compression on the cable. Have someone bend it every foot. If your signal breaks, this is where I like to put the in diode test, which sends some small voltage and the meter beeps at you. So as long as you have continuity, the meter beeps. And if you bend it every foot and all of a sudden you lose continuity on a lot of those meters, then it'll stop beeping and you'll know, hey, I have a cable that's it's right on the line of being severed, and sometimes I get a connection, sometimes I do not. These are the worst problems that we have here, because you might start a calibration, you might get halfway through your calibration till you randomize the loading conditions, and then the load cell starts kiting. And it starts kiting because guess what? When you randomize the connections, you move the cable that you had previously supported during the cal. Check the load cell's zero balance. Cannot stress this enough. If you have a meter, some meters you can just plug the load cell into and check them. Check a unbalanced zero. You can, often put it in different modes, gross, net, some other ones. Some meters have shunt cals. We see a lot of people do shunt calibrations. That is a good internal reference to check the system and the load cell. This load cell tester is really good if you want to check different load cells. If you have a bunch of techs that go out, they use them in the field, someone comes back and says, hey, I didn't overload that. And you say, well, before it went out, the signal output was 0.2, and now after you went out, it's 32.84. That means your tech, overloaded the load cell, or it could have happened in shipping or something else, but at that point that, someone did something and the load cell's really not fit for use. This is where I like the load cell tester a lot. It's something, a multimeter you can use to check resistance, which we'll go over. It doesn't give you the full picture that the tester does. So if you're really concerned with techs or overloading load cells, or if you want to just keep the inventory of your assets and know that they're all good, this is a very, very good tool. So typically what we say here is if the signal output is over 5%, the load cell has either been overloaded or is there corrosion somewhere in the cable. And here's part of it. Is the zero balance acceptable? Yes, no. If not, contact Morehouse. Sometimes we can have the Q&A where it's 6-7%. The first thing that goes is normally temperature compensation. So if you have a load cell with a zero balance of 5-6%, your real risk, the load cell may work fine, but the real risk in all of this is that the gauge factor and more than likely the temperature compensation is shot, and therefore it can no longer correct. So if you don't have a load cell tester, what you can do, this is a quick one. Hey, did I overload my load cell or not? I can use a handheld meter and I can pin, typically we're looking for a balance bridge, 350 ohms, plus or minus 3.5 ohms. And we can pin the load cell. If I'm getting no reading on pins A and D, and that's my excitation line, then I know the gauge is completely shot if I have nothing, if I put the meter on and I have nothing. If I'm getting a high reading, like maybe 360 on A and D, and B and C, I'm getting a reading like 340, then that tells me the load cell's been overloaded. Now, the problem with the load cell, the problem here with an overloaded load cell is basically Young's modulus. You have your stress strain curve. And anywhere after a certain point, like here, maybe with the bridge resistance, we can still tell, right? With a handheld meter, maybe we get the 360 and the 340. When we get further out here, we can no longer tell. So it's on a handheld meter, it's really, really small difference that we can actually detect. And then eventually it goes to zero or open when it's too far gone. So other things, load cell tester, use a load cell tester or another meter to check the load cell zero balance. If you do not have a load cell tester, you can check the bridge resistance with an ordinary multimeter as just shown there, where you can check A and D, B and C, maybe E and F. And back to the 7-step process again, just as a wrap up. Visual damage, does it power on? Is it performing mechanically? Yes, no. If it's not, our adapter's bottoming out. There's some tricks and tips there. That you really should send back to the manufacturer, unless you're a Cal Lab and you get the okay by the customer and really want to dive into it. I'd still recommend sending it to us or manufacturer. I'd recommend sending it to us because chances are if it's bottoming out, we can fix it. Are all wires connected to the cell and meter? That's, visual and handheld. Is the cable common to the system? Something we haven't discussed as much is another diagnostic or another test, if you're trying to troubleshoot and you have two cables, maybe you just swap cables. And if one cable works and the other one doesn't, then you know there's a problem with the cable. I still like the bend test. That's just another shortcut if the cable is bound to the system that you can check with another cable with another load cell. So, it's like A/B testing, right? Load cell meter, what's bad? Something's not working. Well, let's put another load cell on the meter with the same cable. Hey, okay, still not working. Oh, two load cells, chance of two load cells being bad or less. So now we're down to cable or meter. So you can, by deduction processes, you can do that. I just like pinning the meter or pinning the cable from the start at that point to make sure things are good. But, whatever. A lot of times things are as simple repairs such as replacing the cable or something got severed in shipping. So overloaded load cell, here's a cartoon that we did, just fairly, kind of trying to be comical. Why are you so stressed out? Stress strain, and the load cell, I was overloaded. Something to think about. And when we start to define overload, we get a slew of questions. So I'm hoping that this next section here, we can answer some of those questions so you can understand. And if you understand, you probably will know a course of action quicker. And quicker is usually better. Most cells are manufactured to withstand rated safe overload. It's usually found on the manufacturer's spec sheet. On our load cells here, the safe overload for most of them is 150% of rated output. Some are higher, some are less. You have to check the spec sheet. That does not mean internal components will not be altered if the load cell is loaded past a certain point. So a good method to diagnose overloading is to check the load cell's zero balance to ensure it's within the manufacturer's tolerance. That tolerance is typically always less than 1%. And there's a chance a load cell may be overloaded if the zero balance is not within the manufacturer's tolerance and the zero balance has changed significantly from what it was previously. That significant change. So if we have a zero balance that's 0.5%, 1% is the tolerance, and then it changes to 1.5%, and the output of the load cell changed too, that might be okay. But at least you will know that somewhere someone most likely put above 150%, and they basically shifted my curve, right? They shifted the output. You're still within that range, that gray area of 1.5% to 5%. You may consider replacement, or you may say, look, I'm still good. It's still operating. Seems to check out. My temperature variation is not that large, and therefore I'm okay with it. We've seen that go either way. You could have a load cell with a zero balance of 0.1% that shifted to maybe 0.5%. That tells you, yeah, someone probably applied 155%, 160%, real easy. And then if your output shifted, what do you do? Well, as long as they don't continue to overload it and it's still within the manufacturer's tolerance, you're just going to have that shift. You're going to have the bump in the data. More than likely, you should shorten your recalibration interval to make sure that it's okay. If you're on a year and you had a bump, maybe you shorten it to 6 months. Maybe you shorten it to 3/4 of a year. Whatever you're comfortable with is that gives you that peace of mind and sanity to say, okay, we're good. I know that someone did this. As long as we continue to monitor it, we're good. So just some additional tricks there. Results of overloading, we get asked a lot, hey, can it be repaired? Typically the answer is no. And mechanical damage has been done that is not repairable. Permanent deformation with the flexural element engages, which destroys the carefully balanced processing. It's done. You have material that no one really knows how much it's been deformed, right? The residual stresses and strains are introduced into the structure. So going back and saying, hey, You can't calculate a lot of this. So re-gauging it is painful. You can't get, luck, more than often than not, you can't get it right. Past mechanical history of flexure gauge alley back and adhesive is altered. The load cell symmetry is affected, as well as compression and or tension output. And when we say symmetry, that's compression and tension, which means, hey, if prior to my overload, my load cell was reading 4 millivolts per volt, or you can go, hey, it was reading 10, let's say that equates to 10,000. Sorry for my script here, I'm using my mouse. Say that equates to 10,000 pounds. That means, hey, maybe in compression, now we're reading 10,100, and maybe in tension, we were reading 9,900. And same with the millivolts. Maybe we're 3.9 and 4.1. That is a very good indication that someone overloaded the load cell if one mode goes high and the other mode goes low. That's where you want to check and make sure, use the load cell tester to check the zero balance. There's other meters that can do it if you're out there. Agilent 3458, Fluke 8508. There's a lot of other meters that can check the balance, but those are much more expensive than a load cell tester. Strain gauge characteristics are modified, such as resistance and gauge factor, with modified the temperature coefficients. That's typically the first to go, right here, the temperature. And while it is possible to electrically read zero, such as with a meter, just reprogram my meter. There may be other things that are going on that make it not fit for use, so it should be checked out. It is not recommended because this does nothing to restore the effective performance parameters or the degradation to structural integrity. So again, I overloaded something. I took it past, if I'm looking at Young's modulus, I took it past the one region, and now I've altered the properties. And speaking of Young's modulus, here it is. Here's the elastic limit, and here's the graph that what you're looking at. All material has what we call an elastic limit. The elastic limit is a point on the stress-strain diagram where the relationship between stress and strain is no longer linear. If a material has a load applied to it that causes the stress in the material to exceed the elastic limit, the material will no longer return to its original size after load is removed. That's all we're seeing. And eventually you get to break or rupture. This is at, some people may say, oh, I didn't break it yet. This is usually at 200 to 300%, right? And maybe even more. But this is, so right here, this is around our 150, depending on the load cell. And if we're in this tiny region, we likely can measure it in ohms. If we go beyond that, we're really shifting to zero. So something to consider. Causes of material deformation. And here we have sacrificial blocks. You can see this block has been degraded. It's something else that we see in using the adapters. Adapters that are used for calibration should be sent with the load cell. And if this is the adapter that's used with it and it deforms, the recommendation is grinding, but at least you have that same hardness. And what really happens here is material with a lower yield strength than what is being applied will deform until the maximum compressive stress is below the material yield point. Deformation under compressive stress is less than yield stress. And then a steep radius concentrates the force over a smaller area and may cause material to permanently deform. And that's why we recommend compression loading pads. It's also what's happening with a load cell, right? If you're in compression, if you're in tension, you can just pull out the whole web element. So, talked a lot about a load cell tester. It's a tool, we resell them. They are branded. They're made in Israel. By a company, and when we first sold them, just loved them because they save a tremendous amount of time. It's a product that's under $1,000, and if you've been in a lab and you've had bad load cells, or you've been concerned with them, you start asking, what would it cost if a tech overloaded a load cell and we waited a full year till we really found out? We know the output shifted. And then we suspect it shifted, and then the calibration laboratory confirms it. What would that really cost? What type of recall would happen? Would a recall happen? Would it not happen? Would it be intolerance to your specifications? These are all questions, internally everybody has to ask. Is it worth buying a load cell tester to monitor and check my performance? What about my calibration provider? If I send it out, before it goes out for cal, if I send it out, I take all my zero balances, and then it comes back and they're higher. You think the calibration provider overloaded it? We have those. Unfortunately, we overloaded a load cell this year. We always tell the customer it's one of the worst calls you make, can possibly make, because you lost history, unless you grabbed the history and did it on the last run. But yeah, somebody does. We have protocols and stuff in place, but often if you're training new technicians, which we were doing, a new technician within their first 3 months, there's a high probability that they're going to do something wrong. They're going to be trying to pay attention to something else, and they're going to magically, overload the load cell. So it does happen, even at every level. We are not immune to it. So that one. But what if the Cal Lab's not honest and they don't tell you, and then you get that load cell back and you don't know what's been done to it? You send it out. You have the load cell tester. You can send everything out. You can know it's good. When it's coming back, it should be good as well. That's not to say shipping, someone didn't drop it. Also, these load cells, the impact force on them. If somebody drops a load cell, like 3 feet with the smaller ones, that could completely shift. There's force equals mass times acceleration. That impact is quite severe. So like a 300-pound load cell, 500, 1,000. If it's dropped, if it's not packed properly, can be destroyed in shipping, or can be destroyed by someone accidentally dropping it. Just something else. And if you have this slide deck, you can see the load cell videos on our YouTube channel of the tester. It's really easy. You hold the power button for 3 seconds. When it boots up, it will need to be calibrated if you want to take shield to bridge, body to bridge, or shield to body measurements. These are things, the instructions are there. Press on and off with the down arrow. And what that's really doing is it's sensing. It's going through the whole load cell, checking the circuits, checking everything else, and then you can scroll through and you can see all these readings. Input and output resistance. That one you can do with a $20 handheld multimeter. That's load cell tester, doesn't give you much over the meter there. Resistance difference between sense and excitation leads. That's a lot more difficult to do on your handheld, so this would be a win for the load cell tester. Signal output, that's zero balance. It'll tell you that. That's a win. Shield to bridge, again, that's load cell body to bridge, shield to body. These are things a lot of people throw out. All these 4 things, well, not these 4, these 3 things here. These 3 things, people throw out lots of good load cells when it's just some corrosion in the line or the cable's gone bad. So, and the other thing that this will do is, if you wanted to know linearity, you can have this in live mode where it'll actually display linearity. You can put, the full scale on it and see what it reads at 50%, the other one. So if you're wondering how linear my load cell is, that's an added bonus here. We sometimes use it. There may be value in several, but the big value here is really this for diagnostic and keeping some process control on your instrumentation, is that signal output or zero balance. The secondary outputs are like input resistance, shield to bridge, bridge to body, shield to body. That can tell you if you have some problems. Specifically, if you have grounding issues, this can tell you a mega ohm meter costs over $1,000 to diagnose that, which the tester will. So some other things, if the resistance is not in range, there may be a cable or connector problem. There may be internal damage to the bridge of a load cell. Check the manufacturer's specification. Testers show the values within plus or minus 5 ohms. If the sense is too high, 6-wire cell, the sense lines may not be connected. That one people miss quite a bit. If they're wiring cables, they forget to wire sense. Or if one of the sense readings is high, then there's probably a cable error. And typically, if signal output is over 5%, the load cell has either been overloading or is there corrosion somewhere in the cable, which the tester can check for. And then here's where we get to the mega ohm reading here. Load cell insulation resistance specification for load cell to body bridge is usually greater than 5,000 mega ohms at 23C. On the tester, shield to body greater than this. We typically do not run it. The shield is attached to the load cell to prevent ground loops, so the shield or body which generally meet the same specification. All that saying here is when we power this up, and if you want to use this, you make your own cable, and typically we put alligator clip, one cable with an alligator clip that can be connected to the different input on the load cell tester, and then you connect that to the load cell. So you fire it up, do your test, then fire it up and hook the alligator clip on, and you can do these other tests that way. So if you want more info or you have interest in other ones, our next webinar is going to be on the universal cow machine. This is a new webinar, and we're going to conduct that June 8th.